this is the solutions to the study guide, the big review at the end of Module 3. So the first part of the module was about graphing exponentials. So how do I graph an exponential? So I need to identify the parent graph, which is 1/3 to the x, and then 2 points on that parent. So one point is 0, 1, and the other is -1 and 3, and there's an asymptote on an exponential, which is 0. And then there's transformations. So a, in this case, is -1. H also affects the y coordinate. So the y coordinate is going to be changed using both a and h. K is +1. That one affects the x coordinate. So to each x coordinate, I'm going to add 1. To the y coordinate, I'm going to go times -1. That's a reflection, plus 4. So again, -1 plus 1. And then 3 times -1. That's -3 plus 4. And then the asymptote at 0. Add 4 to it. 0 times -1 is 0. Whatever k equals, did I switch? No, sorry. Whatever hk, I got this switched around. So this is really, you probably, k, and this is actually h. I did it right, but I just labeled them wrong. So whatever k is the asymptote, and there. All right, put these on your graph. 1, 3, and 0, 1. There's an asymptote at 4. And then the curve. Now this curve's been reflected. So this is what the curve looks like now that it's been reflected. So there's the curve through the 2 points and the asymptote. The domain for all exponentials. The range goes from the bottom to the top of the asymptote. The y-intercept I'm going to leave empty. It's actually 1, doesn't matter. The asymptote is y equals 4. This is an increasing function, doesn't decrease, and the end behavior, as x approaches infinity, the right end approaches 4. As x approaches -infinity, the left end approaches -infinity. All right, so you have your end behavior, your graph, and the analysis. On to number 2. I want to graph this exponential. So the parent graph is just e to the x, and 2 points on this parent are 0, 1, and 1 and e, and we have y equals 0. Remember that e is a number, 2.7 about. Then look at the transformations. A is 2/3, and k is -5. That is what affects the y coordinate. In the exponent is what affects the x coordinate. So b is equal to 2, and h is equal to +1. That's going to affect the x coordinate, what's in the exponent. So 0, 1, take 0, and you're going to divide it by 2 and add 1. So 0 divided by 2 is 0, add 1, there you go. The y coordinate times 2/3, take away 5. So you need to know what 2/3 take away 5 is. So that's 4 and 1/3, -4 and 1/3. Let's change the next point. The x coordinate, we're going to divide by 2. So 1 divided by 2 is 1/2, plus 1 makes it 1.5. The y coordinate, we're going to multiply by 2/3. Now remember that e is about 2.7. You could even round e to +3. So when you go e times 2/3, take away 5, e and 3 as an estimate, they divide out and leave you the answer -3. So now we have 2 points to put on our graph. The asymptote is what k equals, so the asymptote is at -5. All right, put this on your graph. So 1 and -4 and a third, 1.5 and -3, and then the asymptote at -5. And then connect this. So there's your curve of an exponential. Now the analysis part. The domain is all real numbers. The range is from the asymptote. So that is -5 to infinity. The asymptote is at -5. This is an increasing function. Just leave the y-intercept blank. Never decreasing. And the end behavior, as x approaches infinity, the right end goes to infinity. As x approaches -infinity, the left end is approaching the asymptote, which is at -5. All right, one more for graphing an exponential. So identify the parent function. That's y equals 2 to the x. 2 points on that are 0, 1, and 1, 2, and the asymptote at y equals 0. A is equal to 3, and k is -6. That affects the y coordinate. B is -1, and h is -2. That affects the x coordinate. So to the x coordinate, we're going to divide by -1 and then subtract 2. To the y coordinate, we're going to multiply by 3 and then subtract 6. So there's a point. So again, 1, we're going to divide by -1. So that's -1 take away 2. To the y coordinate, we're going to multiply it times 3 and take away 6. And then the asymptote is always what k equals, which is -6. All right, we're going to take this onto the graph. So -2, -3. -3, 0. The asymptote is at y equals -6. And then the curve, now this curve has been reflected, so that's why it looks like this. So now it's a decaying curve. Now the analysis part. So the domain is all real numbers. The range from the asymptote to infinity. The asymptote is at -6. This is a decreasing function. And the end behavior, as x approaches infinity, f at x approaches the right end, the asymptote. The left end behavior, as x approaches -infinity, the left end is going to infinity. All right, so there's your review on graphing exponentials. Now the next page, graphing logarithms. So again, same idea. Identify the parent. So the parent is just the base and x. Now, if you forget what 2 points are on here, you can inverse. The inverse function for this is 3 to the x. And so you can take a point off of 3 to the x and inverse it. So a point on 3 to the x is 0, 1. So if you inverse it, it becomes 1, 0. A point on the inverse is 1, 3. Inverse it, and it's 3, 1. Instead of a horizontal asymptote, inverse it, and now it's a vertical asymptote. Identify the transformations. So inside, h is -4. That's a horizontal shift. And k is -2. That's a vertical shift. So to each one of these, that's what I'm going to do to change them. So subtract 4 and subtract 2. Subtract 4 and subtract 2. And for this one, whatever h equals is the asymptote. That's where it is now. So those 2 points and that asymptote I'm going to put on my graph. So I got -3, -2, -1, -1. The curve of a logarithm looks like this. And you've drawn your logarithmic curve. The analysis here, there is a domain restriction for a logarithm. So it goes from the asymptote. So that's -4 to infinity. There are no restrictions on the range. The x-intercept doesn't matter. The asymptote is at x equals -4. This is an increasing function, never decreases. And then the end behavior. As x approaches infinity, the function approaches infinity. As x approaches, now be careful, never approaches negative infinity. So the left, it approaches the asymptote. So as x approaches -4, then the function goes to negative infinity. So there's the end behavior of that logarithm. On to number 5. For number 5, identify the parent. So for this one, the parent is 1/2 in x. 1 point on this is 1, 0. And the other point would actually be 2 and -1, because the exponent -1 does the reciprocal of that base, and then x equals 0. Look inside the logarithm, and you can see b is equal to 3, and h is -1. The only thing that affects the y-coordinate, actually, we have a equaling -1, and we have k is equal to +1. So the top affects the x-coordinate, and the bottom affects the y-coordinate. So let's see the change for the x. So 1 divided by 3 is 1/3. Take away 1, which is -2/3. And then 0 divided by -1 is 0. And then add 1. Let's do that again. 2 divided by 3 is 2/3. Take away 1 is -1/3. And then -1 divided by -1 is +1 plus 1, which is 2. And then the asymptote is whatever h equals. So it's -1. Put those on your graph. So -2/3 and 1, -1/3 and 2. Estimate those. Our asymptote is at -1. And then draw the curve, a logarithmic curve, through those points. Now the analysis. The domain is all real numbers. No, it's not. There's an asymptote. It goes from -1 to infinity. The range is all real numbers. I don't care about the x-intercept. The asymptote is at x equals -1. This is an increasing function. And the end behavior. So as x approaches infinity, the function goes to infinity. As x approaches -1, the function goes to negative infinity. So then you have your end behavior off the graph. All right, one more logarithmic function to graph. Number 6. Identify the parent, which is just ln x. Remember that the inverse of that is e to the x. So if I take the point 0, 1, inverse it, or 1e, inverse it, and instead of y equals 0, it's x equals 0. So that's what's on ln x. A is 7/4. and k is -3. That affects the y coordinate. B is -1. That's the only thing that affects the x coordinate. So the x divide by -1. The y coordinate, 7/4 times 0 is 0. Subtract 3 and it's -3. E divided by -1 is -e, like -2.7. And then 1 times 7/4, take away 3. So that might take a little bit of thinking. So 7/4 take away 3. Get common denominators, and you get -5/4. And the asymptote for a logarithm is always what h equals. In this case, h is 0, so it stays at 0. All right, we're going to put those points on our graph. So -1, -3. -e, that's -2.7. And -1.25. Kind of in there. The asymptote is at 0. There's a reflection here. Notice the picture now is on the left of the asymptote. So the picture of this logarithmic curve looks like this because it's been reflected. So there's the sketch of it. And then after you sketch the logarithmic curve, the analysis, the domain, goes from -infinity up to the asymptote, left to right. The range is all real numbers. The asymptote is at x equals 0. This is a decreasing graph. And the end behavior, as x approaches 0, the function approaches -infinity. As in this graph, x does approach -infinity, and so the left end goes to infinity. So there's the end behavior. All right, that's enough graphing, right? There it is, and the analysis. Turn the page. Let's move on from the graphing. Can you work with logarithms? So if we need a calculator, we're going to go on Desmos, okay? Rewrite each one. I'll rewrite each equation in exponential form. So 81 is equal to 3 to the exponent 4. 132 is equal to 1/2 to the exponent -5. How about the other way? Oh, one more here. 8 is equal to the base for ln is e to the 2.08. Number 10, can you write it in logarithmic form? So the exponent is 7/2. The logarithm has a base of 4 and then 128. Here, the exponent is 4. The logarithm has a base of e. That's ln and then 54.6. Number 12, this is a common logarithm. So all I have to do is write down log 10,000 and it's done. So I don't need the base 10 there to write it because it's called a common logarithm. Can you evaluate these by changing the base? Well, some of these I don't have to, so just evaluate it. This answer is going to be 0 because 4 to the exponent 0 is equal to 1. For this one, the exponent here would be -4 because 1/5 to the exponent -4 is 625. For number 15 and 16, you need Desmos. So to type it into Desmos, it would be log 6 divided by log 12. That's changing the base. This is what it would look like. So log 6 divided by log 12. So it would be 0.721. Number 16, since I'm here, log 61 divided by log 8, I think. Is that what that is? Yes? So that gives me 1.977. So again, this was log 61 divided by log 8. Number 17, do you know your properties of logarithms? To write this as one logarithm. So 4 is the exponent. Dividing means, or subtracting means dividing. And again, the exponent on y is 2. Done. Oh, and it has a base of 3. There it is. For number 18, to write it as one logarithm. Inside the parentheses, adding means multiplying. These numbers are really large to multiply, so I'm actually going to apply the exponent 1/3. So the exponent 1/3 means the cube root. So the cube root of 64 is 4. The cube root of 27 is 3. Still have a 2 in front here. Next, now we can do this. If you're adding, you multiply them together. So this is 4 times 3 squared, which is 36. So 3 squared is 9, 4 times 9, and you have your answer. Number 19. Again, I'm going to apply what I can here. So first of all, it's 64 times k to the 5, because that 5 is the exponent for k. And it's the square root. The exponent 1/2 means square root. And that's subtract. And again, the exponent on m is 4. So if I was going to write this together, the square root of 64 is 8. I'd write k as 5 over 2 because of the square root, and then divided by m to the 4th. That's one logarithm. Number 20, the 2 is an exponent for x minus 4. And then when we write it together, I'm going to multiply it. I'm not even going to expand it. So x subtract 4 squared times 3x, and it's written as one logarithm. For number 21, we're going to expand the logarithm. We're going to go in the other direction. So I'm going to write this as an exponent. So that's 4x minus 5 to the exponent 1/3. Then I can write that in front of the logarithm as a product, and that's it. Adding or subtracting inside the logarithm, there's no properties to do anything with that. So we're looking for multiplying, dividing, and exponents. So for this one, it's 3 times. Make sure to always put the exponent in front as you're writing it down. And then when you're dividing, you are subtracting. And there you have expanded it using the product property, the quotient property, and the power property. All right, on to the next page. For 23, again, can you expand this? So the exponent 3 becomes 3 times log. And then I'm going to write the square root of u right away as u to the 1/2. So we have 3 in front. And then I'm going to expand this. So I'm going to go log 5 plus 1/2 log u plus, not plus, subtract because you're dividing, 2 log w. So keep applying it. Whenever you see an exponent, write it in front. Just keep practicing that. And you got it. 24. You have to factor this in order to do anything with it. So that's negative 24, negative 2. So it becomes 3x squared minus 6x plus 4x minus 8. So if I factor this, look at the first two terms. Factor out of 3x, and you're left with x minus 2. Factor out of 4, and you have x minus 2. So I got ln 3x plus 4 times x minus 2. So now I have a product. So I did all that work to get a product so that I can separate it. So 3x plus 4 plus ln x minus 2. So you create a product, and then you can write it as two logarithms adding. All right, can you solve a logarithmic equation? So when you have one log equaling another log, you can remove it and make what's left over equal to each other. Combine like terms, so subtract 2x squared and subtract 12, so it's equal to 0. Factor it, so that's positive 6 and negative 2. Solve it, and then you just have to make sure that negative 6 and positive 2, when you plug it back in, it gives you a positive number inside the logarithm. Both are good answers. Number 26, I need to write this as one logarithm. So that's going to be 12 divided by k minus 5. Then once it's written as one log, that's a 9, right? All right. So once you have that and the bases are the same, then remove the logarithm and then solve what's left over. So to solve this, we're going to multiply both sides by k subtract 5. So that's 12 equals k squared plus 6k, subtract 5k, subtract 30. Make it equal to 0. So subtract 12. Combine like terms. This is factorable. So negative 42 and positive 1, the two numbers are 7 and negative 6. And then each factor has a solution. So the first factor, the answer is negative 7, and the second answer, it's positive 6. Negative 7, when you plug it back into the logarithm, gives you a negative number inside the logarithm. That's a restriction. So negative 7 is called extraneous. Positive 6 is a good solution. When you plug positive 6, it gives you a positive number inside the logarithm. Done. Number 27. Write this as one logarithm. So 1/2 means the square root. So this is the square root of 5c subtract 9. On the other side, when you're adding, you multiply. So that's 6 when you multiply it together. So then remove the logarithms. 5c subtract 9 is equal to 6. Square both sides to remove the square root sign. Add 9. Divide by 5, and you get your answer. And positive 9 is a good solution. Number 28. This is different. We have a logarithm equaling a number. So the step 1 is going to be to subtract 2 to both sides. Get common denominators. So we have 11, take away 6, so that's 5/3. And then we're going to write this exponentially. So we have 7 subtract 5w, 8 to the exponent 5/3. 8 to the exponent 5/3 means the cube root of 8 to the power of 5. So that's 2 to the 5, which is 32. Subtract 7 and divide by negative 5, and you get a good answer. Oh, what did I do wrong here? When you subtract 7, that's actually a positive. So this ends up being negative 5. That's important because a negative times a negative makes it positive inside the logarithm. Number 29, solve the equation. So write this as one logarithm. So we have 2r subtract 3 times. Now 1/2 as an exponent means the square root of 9. And then once you have that, write that as an exponential. So inside the logarithm, when you expand, is 6r, take away 9. And then the base is e to the exponent 7. This is going to require Desmos. We're going to add 9 and divide by 6. So e to the 7th plus 9 divided by 6. So again, e to the 7th there it is. Oh, what am I doing here? Try it again from the beginning. So e to the exponent 7 plus 9, all divided by 6. So 184.272. Number 30. In number 30, again, we're going to write this as one logarithm. So that is an exponent, but I'm not even going to do that. I'm going to subtract 9. I don't need to put it inside the logarithm. So I'm going to subtract 9. And 15 take away 9 is 6. And then divide by 3. So you get 2. Now we're going to write this as an exponent. So we have 2h squared subtract 14h. And it's 6 to the exponent 2, which is 36. This is a quadratic, so make it equal to 0. So we're going to subtract 36 and then divide everything by 2 to make it easier to factor. So the two numbers that multiply to negative 18 and combine to negative 7 are negative 9 and positive 2. Make sure, especially check the negative 9, but a negative times a negative is a good answer. For positive 2 inside here, this actually makes a negative answer, so you should really cross out positive 2. Because positive 2 ends up being a negative answer inside, so the only correct answer there is negative 9. Oh, wait a second. Haha. Negative 9 and positive 2, those are the factors. So it's positive 9 and negative 2. So positive 9 is fine. Negative times a negative, both are fine. So that way they're both fine. No restrictions. How about an exponential equation? So to solve this exponential equation, we're going to write it with common bases. So 1/2 is 2 to the negative 1. And there's already 2 there. 4 is 2 squared with 3d. And 1 is 2 to the exponent 0. So they all have the same base. So we have negative 2. Now we add the exponents when you're multiplying and the bases are the same. And then solve that equation, just looking at the exponents. So add 2, and then when you divide by 6, you could also write the answer as 1/3. For number 32, common bases, that's going to be 3 to the exponent 5. That's 3 to the negative 2. And there is a negative m. I just got to make sure I can see that. That's a negative m, right? And then 3 to the exponent 3, and that's negative 5m. So make all the bases the same. And then a negative times a negative, so that's plus 2m, is equal to negative 15m. Subtract 2m, and then divide. All right, turn the page. Number 33. This is going to require Desmos. So it's 18 to the exponent 3n. Add 4. So it's 53. Write this as a logarithm. And then divide by 3. So that's what we're going to type into Desmos. So it's log. So it's log 53 divided by log 18. Move the decimal, or move the cursor, then divided by 3. And you get 0.458. All right, let's look at number 34. Solve this. We're going to add 5. We're going to divide by negative 6. That makes this fraction positive because the negative divided by a negative is positive. 6 does not go into it evenly. Write it as a logarithm, and then finally add 2, and then use your calculator. That's 5.14. 3. Number 35, isolate the exponential part, so subtract 5. That's 15. Divide, just leave it as a fraction. Can't get the basis the same, so write it as a logarithm. The logarithm is going to have a base of 9 and then 15 over 7 inside of it. Subtract 7 and then divide by 2. That's what you're going to put in the calculator. So I'm going to start with log 15 over 7 divided by log 9. Move the cursor. Subtract 7. Oh, and then we want to, I'm going to highlight, well, let me highlight it and divide over everything. There you go. So I highlighted and then divide everything by 2. So you get negative 3.327. All right, one more, and then we have some stories to end with. All right, so we need to make a choice and write one of these sides as a logarithm. So if I take the left side and write it as a logarithm, it'd be 2x subtract 1. The base is 5, and then you'd write 3 to the exponent, x plus 7. X plus 7 is written in front. That's the product power rule. And then distribute. So we have x log base 5, 3 plus 7. Same thing. Gather the x's together. So 2x and then subtract x log base 5 of 3. Add 1 to the other side to isolate it. And then factor out an x and then divide. So divide by 2, subtract log, base 5, 3. So subtract, divide. So that's what it looks like after you divided it all. So that's what you're going to put in Desmos. If it's going too fast, you need to know where the pause button is. And then you can keep going. And you get 4.386. All right, number 37. Kevin started his new job with a salary of $26,000 and some. Every year, he receives a 3.15% increase, right? And use a continuous exponential growth function. So that's what this is. And then the information, his salary to begin with is $26,550. The interest rate, or the percent increase as a decimal, will be 0.0315. And then after 20 years, and then use your calculator. So it's 26,550 e to the exponent, parentheses, 0.0315 times 20. So his salary would be $49,850.56. Then write a sentence. So after 20 years, Kevin's salary will be $49,850.56. Period. Done. Number 38. A 2018 Chevy Tahoe was purchased for $62,000. After 5 years, the vehicle has a value of $35,000. Write a continuous exponential decay function. That's a continuous one. It's decaying because it's losing value. So we started at, oops, do it right. We started at $62,625, but now it's worth only $35,000. We don't know the decay rate, but that depreciation happened after 5 years. Okay, so now we're going to get R by itself. So first we're going to divide. So it's 35,000 divided by 62,625. And then we're going to write this as a logarithm. So it's 5R equals ln 35,000 divided by 62,625. And then divide by 5 and then use your calculator. So we're going to go ln 35,000 divided by 62,625, and then that's divided by 5. So it is going to be a negative answer because it's depreciating. And then we're going to write a simple sentence at the end. So it's negative 0.116. That's the same as 11.6%. And then a simple sentence. See if I have room. So after 5 years, the Tahoe depreciated by 11.6%. I should have left more room for my sentence. My bad. 39. A contagious disease started, and after T days, and the number of people who have been infected by the disease is modeled by that function below. So there's 350 in the apartment complex. And it says, how long will it take 150 people to be infected? So 150 equals 350, 1 plus 4 times e to the negative 0.07 t. All right, we're going to use Desmos to solve this. I'll show you how. So we're going to write it as a function of, well, I think we can write it as a function of t, and I think it will solve. Do it okay? So let's see. So that's 350, and then it's 1 plus 4e to the exponent negative 0.07 t. And then for the second one, I'm just going to go y equals 150, and then I'm going to look for that on my graph. So it graphed it fine with t, and we're looking for where they intersect, the two of them, and that will solve the equation. So how long will it take to get to 150? And the answer is about 16 days. So in 16 days, 150 people will become infected. So we use Desmos to solve it. In 16 days, about 150 people will become infected. All right, turn the page. Here's the last of the review. Number 40, Sharon invests $2,300 in an account. and it pays 4.25% compounded weekly. So our formula for compounded weekly looks like this. There are 52 weeks in a year, so that's what the formula will look like with 52. So we have 2,300. The interest rate is 0.0425 divided by 52 weeks, and then 52 weeks times how many years? 18 years. So that's how many times it's being compounded. Use your calculator. So this is what it would look like. So 2,300, 1 plus 0.0425 divided by 52 to the exponent 52. We need parentheses here. 52 times 18. So that's how much money is in the account. $4,941.14. Come back here. Write a simple sentence. After 18 years, there will be $4,941.14 in the account. So after 18 years, there will be $4,941.14 in the account, period. All right, last three questions are regression questions. On January 1st, 2013, a deposit of $600 was put in the new investment. The table below shows the balance. It says use an exponential growth regression. So that's A times B to the X. That's the model we're going to use. We're going to use 0, 1, 2, 3, 4 when we put it. And then we're going to create a model. And then we're going to answer the question, what year the account will earn $4,000. All right, let's put that into Desmos as a table. So clear this, click plus sign and table. In the first column, I'm going to put 0, 1, 2, 3, 4. In the second column, the money is $600. Don't put a dollar sign. 675.11, 771.64. 865.79 cents, 980 and 26 cents. All right, so we have a table. Next, we're going to do a regression by going Y in the squiggly equal sign on the top left corner of your keyboard. And then we're going to type in A, B to the exponent x1. Oops, this needs to be y1. So Y, our column is y1 and x1. So just type in that. That's an exponential growth model. Notice the r squared score is very close to positive 1. So we have a good model. So we're going to write that equation down. So that equation A is like 600. The base is 1.13. And to that exponent, so this is what it looks like. I wrote it T for time. And then 4,000, I need to solve this equation. When is that equal to 4,000? What time? So we're going to use Desmos to do that. So in the second window, third window, we're going to type in y equals 2,000. No, 4,000. And then see where we're going to zoom out until I see that line. So there's 4,000 right there. Zoom in until you can see the point of intersection between them. Don't hit the y-intercept. So how long would it take to reach 4,000? So it's there 15 years. So come back here. 15 years from here, 13 plus 15 is 2038. So in 2038, the account will reach $4,000. Number 42. The table below shows the gym membership sales in each of its first 6 weeks. Use a logarithmic regression, that's this, and then find the number of gym memberships sold in 20 weeks. Okay, so that's what we're looking at. So let's put the table in again. So clear this. Let's get a fresh table. So again, the first column's 1, 2, 3, 4, 5. And then 162, 187, 199, 211, 220. And then the model is Y, squiggly, should be Y1, sorry, squiggly. And then we go A plus B ln X1. That's the logarithmic growth. Notice we have a good R squared score. A is 162. B is 36. I'm just rounding. So we have our equation. I put it in terms of t for time. And then what happens when x is equal to 20? So in this case, it's t actually that's equal to 20. So we're going to type that in. So on Desmos, we're actually going to type in x equals 20. And then we're just going to look and see where the two intersect. So the red and the blue, at 20 weeks, how many members do we have? It's a lot. Oh, 200 and, sorry, I was reading it wrong. 268. That makes sense? I was reading 20,268. All right, 268. Write a simple sentence. So in 20 weeks, the gym should have 268 memberships. All right, one more left. So in 20 weeks, the gym should have 268 memberships. All right, 43. A population of fish is deposited into a local lake. Determine whether an exponential or a power model. So exponential looks like this, or a power model looks like this. So they're similar, just the base and the variable are switched around. So which one's a better model for this? So let's put it in C. So again, we need a fresh table and see what the answer is. So we have 1, 2, 3 to 6. So 1, 2, 3, 4, 5, and 6. We started with how many? 78 fish, 92, 100, 106, 113, and 118. So there's, then you can kind of see the points that I put there and the kind of what's happening. So there's the points. So the first model is Y1 squiggly. It's the exponential model. So it has an R squared score of 0.947. I'm going to quickly do the other model, squiggly. Oops, squiggly, there it is. And this was AX1 to the exponent B. That one has a better r squared score of 0.998. So I'm going to get rid of u, and I'm left with the better model. Oops, what did I get rid of? Oh, I still have, do I still have, this is, which one's the, let's try it again. This, get rid of u. There, the power model is the better model with a better r squared score. So we're going to use the power model. So A is 78. And the exponent would be 0.23. And then use that model. So T is the number of weeks. So that's A and B. And then we want to know, use the equation to approximate the number of fish after 1/2 of a year. So half a year is how many weeks? So to go 52 divided by 2. Can I do it? Let's hope. So that's 26 weeks. So how many fish will there be in 26 weeks? Let's use our calculator. I'm just going to type in x equals 26. And then find the point of intersection. So at 26, the answer is there'll be 164 fish. So in 26 weeks, there will be 164 fish in the lake. Or half a year. So in 26 weeks, there will be 164 fish in the lake. And that's it. You did the review. I'm proud of you for finishing your work. Until next time. Mr. G Math, over now.